Here's a quick overview of what I'll discuss in this session. We're talking about sensor switches, and we'll talk about the normal status of the switch, some various types of switches, how they work, and some details about them that are useful and interesting. When we say the normal status of the switch, what do we really mean? Well, we just mean how are the electrical contacts when there's no physical stimulation. In other words, if the switch was out of the machine and it wasn't plugged into anything, it wasn't in the machine, it was just sitting on a bench. Okay, so you can think of it as the switch being at rest, but really it's just the natural state as the thing was manufactured. That's the normal state of the switch. It's the non-activated state where you haven't pushed the switch. So a limit switch, for example, would be in its normal state when nothing's touching it, contacting the switch and making it change from its normal state. And a lot of time these switches have a spring that returns them to their normal state. In a proximity switch, when the target's far away, then nothing's being sensed, and that's the normal state. In a pressure switch, where there's low pressure, so the pressure switch is not activated, it's in its normal state. In a level switch, for example, when the tank level is low, then that would be the normal status of that switch. Temperature switches, for example, might be when there's a low temperature, when it's cold. A flow switch would be off when the fluid flow has stopped. Now the normal status of the switch should be represented on a schematic diagram and should be shown so that it's clear which is the normal status. You don't show the activated status on a schematic drawing. Now you have to be careful, because once the devices are installed in a machine, they may be totally different. For example, in a microwave, the normal status of the switches that sense when the door is closed is actually when you have the door open. And that's the normal status. But when you close it, most of the time that your microwave is sitting there, the switches are in an activated state. It doesn't mean that there's current flowing through them necessarily. It just means that current can flow through them, or not. The switches are being pressed. In other words, they're being activated in the condition where the microwave door is closed. Their status is different. If I were to take apart a microwave and pull a limit switch out, for example, that's the state it will be in, separate from the microwave. That's the status it would be in when I put it in and open the door. And so that's its normal state. But the usual state in a machine may be very different. A switch may be activated most of the time. So here are some symbols to show what various types of switches look like, their standard schematic symbols, and what they would look like if they're normally open, that's on the left column, versus normally closed. And you can get a switch either way. Some switches are made in a not passing power in its normal sense, that's a normally open, or passing power in its normal sense, that's normally closed. And so you see that the symbol for a pressure switch is a little different than that for a level. The pressure switch is a half circle. A level switch's standard symbol is a circle. A temperature switch has an odd square squiggle line on it, and then a flow switch has something that looks kind of like a flag on it. But these are just standard schematic symbols, and whatever the usual state of the switch is, even if it's not that way when it's installed in the machine, is what should be shown on a schematic diagram of the process. A hand switch is exactly what it sounds like. It's a switch that's pushed by hand, so it's a push button or some such thing. And these can either be activated or not activated. So you see the button on the left with it popped up. The activated state is where it's being pressed in, you see. And so there are actually two sets of terminals on this switch, a normally closed set and a normally open set. And what happens when you press the button is the normally closed set breaks and the normally open set makes. In other words, power can flow through from one normally open terminal to the other when the switch is in its active state. But when the switch is in its normal state, only the normally closed terminals are in electrical contact with one another. Limit switches are very common. They're different than hand switches. They're operated by the machine most often. And basically they detect positions of things, positions of doors, or there's just all sorts of things. You can have a part go by and trigger a limit switch, although a proximity switch is usually preferred when parts are going by, because you usually prefer non-contact methods of detecting parts. But there's often times where a limit switch is useful. If you have a four-door car, you have at least 4 limit switches in your car. They may not look exactly like this, but they certainly do change their status when the car door is open so that the dome light can come on. Now, if the switch normally passes power, then it's normally closed. In other words, when it's the lever's not being pressed on it, it's normally passing power. If it's normally open, then it's not passing. Now, that's a simplification, because in reality most of these switches actually have a normally open and a normally closed set of contacts. And so what happens is the common terminal is electrically connected to the normally closed terminal. When you then press the switch and activate it, it switches so that the common terminal is connected to the normally open terminal. And of course the active state is with the lever being pressed. And typically these are the type that will have a spring return, where you release the lever, it'll come back away from the switch body and go back to its normal state with common connected to the normally closed terminal. Proximity switches are usually preferred for detecting parts, and they're used for non-contact detection of items. And so they either use optical means or magnetic, or there's even capacitive sensors. There's many different types of these non-contact proximity switches. Now usually when it's a light-based system, it's really called a photo eye or a photo switch. But when it's either capacitive or a inductive sensor, which can sense, well, capacitive can sense many types of materials. Inductive only senses materials that can, carry current and have current induced in them. In that case, that's usually what you refer to as a proximity sensor. But proximity switch standard symbols are shown there, one normally open and normally closed. Now usually in this type of sensor, you don't have a normally open and normally closed set of contacts. Most of the time you either have, usually it's just a normally open switch, and then when it senses something in front of it, then that switch closes and it goes from false to true. But you can get it the other way around, where it's normally closed, and then in the active state, when it's sensing something, then it opens up. Pressure switches, of course, are used to detect here's the problem. When students think of a pressure switch, they focus on pressure and they think, well, pressure is a continuous variable, so how is this an on-off type thing? Well, the switch has to be set for one particular level of pressure. Some switches are adjustable, especially industrial switches. Some are not. It just depends on how they're made and what they're for. But essentially, these will turn on or off when going from one pressure to another. So there's a threshold above which the pressure switch is on, say, and below which it's off. As I said, that could be reversed. But the point is there's a threshold. And a lot of times this threshold, just like in temperature sensors, it's different going up than coming down. The problem was, if I say I want this pressure switch to come on at 100 psi exactly, well, when I get close to 100 psi, just the very slightest fluctuation below will cause the switch to go off, and just above will cause it to go on. It's possible it could oscillate quite a lot, and we want to avoid that. So not a lot, but some deadband is usually included, so that, say the switch goes on at 101 psi, but it doesn't go off until the pressure drops to 100 psi. So you see there's a 1 psi deadband where the switch does not change state. Level switches they come in many different varieties. What's shown here is one particular type which uses resonance and a tuning fork and so forth. A fairly complicated level switch, but there's many different types of level switches. This type, what will happen is the resonant frequency of the fork changes when it's in contact with liquid or anything of substantial mass, and so that can be detected. But there are float types, there are just scads of level type switches, and again the standard symbol is the type with the circle at the bottom of the switch there. There are other types of level switches as well. A paddle wheel is not a real common type, but it's a simple idea. The idea is that you have a paddle that's slowly rotating inside of a vessel, and when solid material comes up, it increases load on the paddle, and you can sense that. So you can just have a torque-sensitive switch, essentially, that actuates when there's a certain level of torsion on the paddle wheel. So that's one way of doing it. Paddle wheel sensors are actually also used for flow measurement, and not the same types, of course, but a paddle wheel design can be used to, if you imagine a chamber where the only way to get through is by rotating a paddle wheel, if you count the number of revolutions and you know the amount of displacement for it, you can actually count or measure flow rate. But then that's measuring a continuous variable, whereas here a paddle wheel is being used to measure whether the level in the tank has come up to the level of the paddle wheel. So the paddle wheel would have to be mounted rigidly in the tank at a particular height in order to detect that level is above or at the level of the paddle wheel. Ultrasonics can be used for measuring level as well by just having a transducer and a sender and receiver essentially that sends an ultrasonic signal, sound signal, and receives it. And when there's something in between the gap that changes, either the response time or various different parameters that can be measured. But ultrasonics can be used for measuring the level in a tank as well. And typically these are on-off because either there's something there changing the speed of transmission or the frequency or something of the signal, or there isn't. There are many different types of level switches. One way to make a level switch is just to use capacitive proximity sensors, and you can see here a rail where there's a couple of sensors. They're the white barrel objects above and below at different levels in the tank, and what these do is simply sense the liquid when it rises or falls to that level. There are also conductive switches. If the liquid being measured is conductive, then two probes that are separated can use the liquid as a normally open switch, where when the liquid comes up it closes the contacts and thereby pulls in a switch so that the signal can go into a PLC to let it know that the level has reached wherever the height of the probes are in the tank. Temperature switches, I don't have a good picture of one here, but a temperature switch, usually they're set up to be open when below a certain temperature and closed when above a certain temperature, but it just depends on what type you get. They typically use a bimetallic strip so that as their temperature changes, it's a very mechanical change. The disc essentially will snap to a different configuration and make electrical contact and close the switch. But these have to be set so that, or designed so that they close at a particular temperature. And there's often a lot of deadband, as I mentioned, built into these, so that the switch doesn't, just go to, say, 300 degrees and just sit there and turn on and off as the temperature fluctuates very slightly around that temperature. And it's part of this is due to just the way that they're made. There's some deadband built into them where it doesn't respond over, it doesn't change state over a certain temperature range. And in this case, it's actually a desirable side effect. So you might have, say, a 5-degree temperature deadband, so that the switch doesn't turn back off until it reaches well below 300, say 295 degrees. And so that helps avoid problems with the switch turning on and off too often. And if you're using a temperature switch, you're usually not using one to measure a temperature extremely precisely. You just want to know that the temperature is right about a certain level. If you wanted a more precise measurement, often you would switch to a thermocouple, which could give you a continuous temperature reading, or an RTD, a resistance thermal device, that can give you a more precise measurement but over a more limited temperature range than the thermocouple. But both of those devices give you continuous measurement, whereas a temperature switch turns on at one temperature and off at a close temperature. Flow switches are typically on or off as well. Some flow sensors sense the flow rate or sense various things that can allow you to calculate the flow rate. But a flow switch is a type that is either on or off, and a lot of these incorporate paddles. Now it's a little confusing because some sensors use a paddle where the farther the paddle is bent by the flow, the higher the signal, the higher the flow rate. But some are set up as switches where if the paddle is pushed at all, then it's sensed and is either open or closed, and thereby serves as a switch.